Hi, this is Mrs. Cribb, and this is a tutorial on doing the dual nature of light problems that are in the Honors Quantum Theory homework sheet. I will have given this sheet out to you in class, or I'm about to give it out to you in class. And the top part gives you the formulas that you're going to need, including this one right here, which relates c, the speed of light, 3 times 10 to the 8th meters per second, is equal to lambda, which is the wavelength, times nu, which is frequency. However, we're going to use an F for frequency rather than this nu symbol. And Planck's equation, the energy of a photon of light, photon little packets, is equal to Planck's constant, which is this value here, 6.626 times 10 to the negative 34 joules times seconds, times frequency again, nu. We're going to use the F for frequency. So these equations are on this page. Notice that velocity is down here in Debray's equation. We're not using that one. Okay, I'm going to work out the first 3 problems here, and then I'm going to do another example problem. Okay, on this sheet I will have made a copy of the first 3 problems when I expand it. The first thing you need to do is write down the equations that you know. So energy equals Planck's constant h times F for frequency, and I'm going to give it to you in this format on the test. You will always be given Planck's constant as well. Now this formula you'll be given as well as Planck's constant. 6.626 times 10 to the negative 34th joules times seconds. And the other formula relates the speed of light to the wavelength, lambda, and the frequency. You will also always be given the value for the speed of light, which is 3 times 10 to the 8th meters per second. You may remember that from physical science. I want you to also remember that frequency, the units for frequency, are 1 over seconds, or s to the negative 1 power, or hertz. All those things are the same. We're going to mostly be using this one right here because it works best in our calculations. All right, now let's look at this first problem. The threshold photoelectric effect in tungsten is produced by the wavelength 260 nanometers. Give the energy of the photon in joules. And that is the unit for energy, joules. Hopefully you remember that. So what I usually do is write down the formulas that I have and fill in all the information that I know. Okay, I know energy is equal to Planck's constant, 6.626 times 10 to the minus 34 joules rather, times seconds. All right, joule seconds. All right, I don't know the frequency, so I'm going to need to calculate the frequency or just put it over here. So what I'm going to do is take the formula that I do know, because the information I was given was wavelength, and that is this right here, wavelength. And I already know from here the speed of light. So I'm going to change this over so that this is a frequency formula and put it in place of this frequency over here. So just divide by the wavelength on both sides, and then this cancels out, so that frequency is equal to c over the wavelength. Now I'm going to show you something else. On the notes that I gave you here, this is the honors additional notes. On the second page, you will see not only the colors of light, you'll see the wavelengths of light given in nanometers, the information about the quanta from the photons from Planck's constant, and the energy formulas. Again, you'll see the F there instead of the nu, but you'll see the different forms that relate the speed of light and frequency and wavelength. All these forms are possible, but it's just the same equation that you have to manipulate to be used in whatever form that you need. So now that I know that frequency is equal to the speed of light over the wavelength, I'm going to put this in place of the F that was right there. And so now I have 6.626 times 10 to the minus 34 joules times seconds times c over the wavelength. Okay, so let's fill in every one of our numbers and finish our calculation. 6.626 times 10 to the negative 34 joules seconds times 3 times 10 to the 8th meters per second divided by, the wavelength is 260 nanometers. Now hopefully you'll notice that we have a problem. We have meters on the top and nanometers on the bottom, so I need to do a unit conversion. So what I'm going to do is go ahead and just do the unit conversion here. I could have taken the 260 and changed it to meters up here if I wanted to and put that down, but it's easy just to go ahead and write it here. So multiply this by the conversion factor. Alright, nanometers on the bottom, so I need to put nanometers at the top, and there are 10 to the 9 nanometers, the billion, remember, nano 9, in 1 meter. Now you can see in the numerator over here, and denominator over here, meters, they cancel. Nanometers cancel here, and nanometers cancel here. That's the numerator and the denominator. Seconds, right here in this denominator, cancels with this seconds in a numerator, because that's, anything over 1. The only unit that doesn't cancel is joules, and that is what I need for energy. I need joules. So I'll put all of this into my calculator, and I get let me do my raw answer. I'm going to tell you exactly how I put it in my calculator. 6.626 second function e negative 34 enter times 3 second function e 8 enter divided by 260 enter times 10 up caret 9 enter, and I get 7.6454 times 10 to the negative 19 joules. Now I have to do significant figures. When you do significant figures, do not use Planck's constant. Do not use the speed of light. Use the only value that you were given within the problem. And that value has only 2 significant figures, so my answer can only have 2 significant figures. So it's 7.6 times 10 to the minus 19 joules. That is the energy of this photon, of this light with a wavelength of 260 nanometers. Okay, let's do number 2. A mercury lamp emits radiation with this wavelength. What is the frequency? Okay, so I'm going to go back up here and see that I changed the formula for frequency. Frequency equals the speed of light over lambda, and I'm going to use that. Frequency equals the speed of light over lambda, so I don't have to do anything else with changing. Speed of light is 3 times 10 to the 8th meters over seconds, and the wavelength is right here. 4.36 times 10 to the minus 7 meters. I don't have to do any unit conversions because meters and meters are the same. They cancel. Notice that when I cancel them, I have a 1 left, and the s is still there. So it's 1 over s, which is great because remember I told you that 1 over s is a frequency unit. So now, just put that in my calculator. I have 3 second function E8 divided by 4.36 second function E negative 7, and I get 6.8807 times 10 to the minus 7 meters. I got to figure out my sig figs. The original answer in the problem, the original amount in the problem in meters has 3 sig figs, so I need 1, 2, 3 sig figs. So 6.88 times 10 to the minus 7 meters, and this is the final answer for question number 2. Nope, not meters, sorry. Per second. That's the unit that's left right there, not meters. I'm figuring out frequency. So let me get rid of this right here. There we go. It's per second. There we go. All right, number 3. The brilliant red colors seen in fireworks are due to the emission of light with wavelengths. Okay, the wavelength of this light is 659 nanometers. Calculate the frequency of the red light. This is the same kind of problem we just did. Frequency equals speed of light over the wavelength. Speed of light, 3 times 10 to the 8th meters per second. The wavelength of this light is 659 nanometers. Again, we have a problem. Houston, we have a problem. Okay, meters, nanometers. I need to get rid of the nanometers. What in the world is that? There we go. Okay, so in order to do that, I'm going to need to do my unit conversion. Do it in another format. My bridge notation. Nanometers in the bottom, it needs to be on the top. There are 10 to the 9 nanometers in 1 meter. Now, nanometers in the denominator, nanometers in the numerator, they cancel. Meters in the numerator, meters in the denominator, they cancel. Remember that meters now is just a 1 over S. 1 over S is the new unit. That's what frequency means. So let's do this calculation. 3-second function, 8, enter. 3-second function, EE, 8, enter, divided by 659 times 10 up caret 9, enter. And the answer is 4.55235 times 10 to the 14th. And the only unit I didn't cancel is 1 over seconds. Okay, significant figures. I need 3 significant figures because that's the only value given within the problem. So 1, 2, 3, 4.55 times 10 to the 14th, 1 over seconds or hertz. Remember, you may have to round if this number is a 5 or a 6 or something else. Don't forget about that. That is still important. Now the next thing I'm going to do is give you a new one. Let's see. Okay, we're going to do the example problem that is in the Honors Quantum Theory homework sheet, and it's right before question number 11. So there's an example problem. I'm going to do that right now. So this comes from the Honors Theory homework sheet. Okay, and this is the example problem. It comes before problem number 11. Okay, it says a certain light has an energy, so we have a light with an energy that is 5.0 times 10 to the negative 19 joules. What is the wavelength? That's the question. What is the color? That's another question. And it says to see the chart in your notes. What is the frequency? Okay, so you're going to need to answer all those questions. So energy equals Planck's constant times frequency. Okay, I'm going to just, since I need to figure out the frequency, I'm going to change this formula to figure out frequency. So this goes away, so that frequency is equal to the energy over Planck's constant. So let's go ahead and figure out the frequency. Energy is 5.0 times 10 to the minus 19 joules. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Notice that The joules and the cancel in the numerator and denominator. That just leaves seconds. So this is going to be a 1 over the seconds. That's going to be my unit. All right, so let's put this into our calculators. It's going to be 5, second function EE, negative 19, enter, divided by 6.626, second function EE, negative 34, and the frequency that I get is 7.546 times 10 to the 14th per seconds. Okay, significant figures. Okay, I was given 2, so I need 2. So 7.5 times 10 to the 14th, 1 over S. That is the frequency. So this question has been answered. All right, now I need to know the wavelength. Okay, so C equals wavelength times frequency. Right? We got that from our notes. And so let's change it to wavelength. I'm going to divide both sides by frequency now. So the wavelength is equal to the speed of light divided by the frequency. And I'm going to verify that and show it to you in, let's see, here. Wavelength is the speed of light divided by frequency. It's right there. Wavelength is the speed of light divided by frequency. All right, now let's just put the values. 3 times 10 to the 8th meters per second divided by the frequency of 7.5 times 10 to the 14th, 1 over S. Okay, this is where the unit's going to come from. And there's the numbers. Okay, let's go ahead and get the numbers out. 3 second function EE 8 divided by 7.5 second function EE 14. I get 4 times 10 to the minus 7. Okay, what's my unit? Okay, over here what you have is meters over seconds divided by 1 over seconds. It's a complex fraction. To solve it, you do the inverse. Seconds over 1. Seconds over 1. So you multiply the numerator and the denominator by that inverse. This cancels, this cancels, this cancels, this cancels. Because of numerator denominator, the only thing that didn't get cancels is meters. So the wavelength is in meters, and so that's this question. The only problem is it also asks me the color, and when I go back and look at my notes, the wavelengths are all in nanometers, so I'm going to need to change my meters to nanometers, and then I can look at that chart. So 4 times 10 to the minus 7 meters, do a unit conversion. Meters is on the top, so it has to be on the bottom. 1 meter is 10 to the 9 nanometers. 9 nano meters cancel. So 4 second function EE negative 7, enter, times 10 up caret 9, and I get, I knew it would be in this area, but 400 nanometers. Okay, that's another wavelength. These guys are equal to each other. So now I can answer the last question. What color is this light that has this amount of energy? So go back to my notes. I have 400 nanometers. Well, look at here. That means my wavelength of light is 400 nanometers. That means I must be seeing violet light. So I go back over here and give myself that answer. The color, violet. That is what I'd be able to see. There, that is how you calculate the wavelengths of light with the energy and the frequency, and even find out the color on the visible spectrum. I hope this will help you, and good luck on your homework.